Remember, Maths Extension 1 is an extension of Maths Advanced, so many of the topics in MX1 course build on the topics you'd learn from the Maths Advanced course. So yeah, being familiar with the Maths Advanced course is very important for the Extension 1 course, and don't neglect Maths Advanced because a good chunk of Extension 1 is built upon Maths Advanced. So a key part of the Maths Extension 1 course is the Advanced course. So as much as I enjoy teaching you MX1 integration techniques, like integration by substitution or finding volume of solid revolutions and things like that, I can't really do that until we talk a bit more about Maths Advanced integration. But what we can still do is that related to MX1 integration. So part of the calculus topic in MX1 syllabus requires you to be able to integrate expressions that lead to inverse trig functions and integrate sine squared x and cos squared x. So we're actually narrowing down this calculus syllabus just because you guys need to talk a bit more about the advanced calculus part in order to do some more of the MX1 specific calculus, particularly application sort of questions. So what I'm going to do is talk about things that are related to the MX1 integration topic. So integration and differentiation are opposite operations, and I'm sure you would have heard the term integration before. Quite often you would have also talked about things like antiderivatives, and it's quite closely related, or you could even think of them as the same thing, integrals and antiderivatives. Although they talk about fundamentally different things, and it's very interesting why they're related, because one thing you're talking about rates of change, and other thing we're talking about like area. Why should they be related? That's interesting, and that's something called a fundamental theorem of calculus, which is a bit beyond the scope of the course, but if you're interested, feel free to investigate. So yeah, if we know how to differentiate inverse trig functions, we can actually go the other way to get inverse trig results by integrating. So because we're relying on the fact that dy dx, that differentiation is the opposite of integration. So if we see something that we know is a result of differentiation, we can actually use that to figure out what the original is. So that's going to be integration. And I'll talk about what that means in a second. So in the Year 11 course, you learned about differential calculus and how to find derivative of an equation. And the syllabus stop point in the course is find derivatives of inverse functions by using the relationship dy dx equals 1 over dx dy. We need either directly use that relationship or use the chain rule. They're actually quite related. This is pretty much an effect of the chain rule, but we can use that to figure out certain integrals which might not be that easy at first glance. So from Maths Advanced, you should have also learned that d by dx of sine x is cos x, and d by dx of cos x equals negative sine x, and we'll be using that properties in just a second. So because we know how to deal with those things, and we have that specific syllabus stop point, we can actually use that to differentiate inverse trig functions. So in terms of, before we jump into some calculus, let's look at some inverse trig functions. So things like sine inverse x, cos inverse x, tan inverse x, or you might see it as arcsine, arccos, and arctan. But we want to try and differentiate these things. How do we differentiate it? That's the question that we want to deal with here. Well, to do that, we can actually use these properties of like inverse trig functions alongside the properties of calculus. So what I mean by that is, I'll do one example. I'll do sine inverse x, and cos and tan is very similar, well, particularly cos is very similar. So I'll do sine inverse x, and hopefully that should clarify things, and you should give cos inverse x a go on your own, or you can look it up. It's, again, these sort of derivations aren't something that you expect to do each time you use them. It's just good to be familiar with, and it's a good technique to be familiar with, although it's very unlikely that you'll be asked to reproduce something like this in the exam situation. So let's say we define an equation, y equals sine inverse of x. If we take the sine of both sides, we end up with sine of y equals to x. Now, I'm not going to be too careful with like boundaries and limits, as in domains and ranges of these functions. That's something for you to think about, and that's actually a very important part of this, but just because this is sort of a crash course thing, I don't want to spend too much time thinking about it. It's not too difficult. We just have to remember that sine inverse of x is trapped between a certain domain and a certain range, and we have to account for that whenever we're doing these sort of things. But yeah, we've got sine y equals x. Now I'm going to do something interesting. I'm going to take the derivative of both sides. So I'm going to say d dx of sine y equals d dx of x. Now if we take the derivative of both sides, what do we end up with? Well, we end up with, on the right hand side, it's pretty straightforward. What do we get when we take the derivative of x? It's just going to be 1. So on the right hand side, we're just left with 1. On the left hand side, we actually have to use the chain rule. And the reason for that is because this sine y is not in terms of just x, it's in terms of y. So we're going to have to use the chain rule. And it's very similar to what you would have seen in related rates, where you take the derivative of something that, so you take the derivative with respect to something that's not directly in the equation, but still related to it. So what you have to do is multiply by dy dx in this case, and then you multiply that by the derivative of the function itself, so cos y. And if you're curious about where this came from, it's literally what you would have done before in your related rates questions. It's a product of the chain rule, so it is a consequence of the chain rule. So dy dx equals dy dx cos y equals 1, and so if we rearrange this, we get dy dx equals 1 over cos y. Right? And interestingly enough for us, we can actually express this cos y in terms of x, and we want to express it in terms of x. So to do that, what we're going to use is the Pythagorean identity. So if you guys think back to your trig identities, the most famous one, or the most commonly used one that you would have seen, is sine squared y plus cos squared y equals 1, or it's called the Pythagorean identity. And so then we end up with cos squared y, if we rearrange for it, is going to be equal to 1 minus sine squared y. And so if we square root both sides, we get cos y equals square root 1 minus sine squared y. And we have to be careful with positive and negative signs here. For now, I'm going to say it's always positive, and just believe me for now. But I think if you go back and have a think carefully, you should be able to see why it is always positive. And so we get an expression for cos y in terms of sine y. But where have we seen sine y before? We saw sine y here expressed as just equal to x. So we can actually replace this sine squared y with the square root of 1 minus x squared. So we've actually gone ahead and expressed cos y in terms of x only. So cos y equals to the square root of 1 minus x squared. And so dy dx equals to 1 over the square root of 1 minus x squared. And so we're done. That's how you find the derivative of sine inverse of x. The derivative of sine inverse of x is 1 over the square root of 1 minus x squared. Now that's a known result. That's not something that you have to derive each time, but just know this is how you would get to it. You have to use the chain rule, you have to use a Pythagorean identity, and you end up with this result. And you can use a very similar approach to find that for cos inverse of y. Just give it a second to load. Yeah. So, these are your results. So d by dx of sine inverse of x is 1 over the square root of 1 minus x squared that we showed. D by dx of cos inverse of x is the same, but with a negative sign. And d by dx of tan inverse x is 1 over 1 plus x squared. These results, I believe, are on your formula sheet, so they're not something that you have to memorize. And the derivation is not something that you have to be able to reproduce, but just know that that is the way that they're derived, and that is a possible technique. Now that we know that, we can go the other way and integrate those values to get some of our standard integrals. Because we know that when we integrate, it's the opposite of differentiating, and differentiating is the opposite of integrating. So if we find that we're asked to, so we're not given this sine inverse of x, cos inverse of x thing, we're just given this 1 over the square root of 1 minus x squared thing, and we're asked to integrate it. Well, we know what's the function that that we get when we try and what's the function that we get when we differentiate sine inverse of x? well, it's 1 over square root of 1 minus x squared. So the integral of that has to be equal to the sine inverse of x. So we can go the other way. And we can actually generalize it for not just 1. Now, it's not too hard to get from here to here, but I won't focus too much on the details. It's just a matter of factoring out like a factor of square root of a. Factoring out a factor of a squared from the inside the square root, but again, not too hard there. Okay, so moving on. In the Year 12 3-unit course, you'll need to know how to integrate sine squared x and cos squared x, but how do we do it? Now the answer lies in the cosine double angle formula. So let me show you how you would approach this. Okay. So if we have cos 2 theta, that's not too hard to integrate. We know how to we know how to integrate cos theta, which is just going to be sine theta. So cos 2 theta, when we integrate it, is going to be 1/2 sine 2 theta. Not too difficult. So what we're interested in is how can we integrate something that looks like cos squared theta or sine squared theta? The answer to that is try and turn it in terms of this thing. Now, how do we relate these two quantities? Well, that's by using our cosine double angle formula. So if we use the double angle formula for cosine, it's cos 2 theta equals cos squared theta minus sine squared theta, just from your trig identities. And so that's going to give us, so that's going to show that, let's say we want to integrate cos squared theta, we're going to say cos 2 theta equals cos squared theta. First time we're going to leave as it is. Because we want everything in terms of just cos squared theta, what I'm going to do is use the Pythagorean identity to express sine squared theta in terms of cos squared theta. So Pythagorean identity says sine squared theta plus cos squared theta equals 1. So we end up with 1 minus, so we end up with sine squared theta. If we want to express it in terms of just cos squared theta, it's equal to 1 minus cos squared theta. So we get cos squared theta minus 1 minus cos squared theta. Like that. And so we get cos squared theta minus 1 plus cos squared theta. And we end up with cos 2 theta as being 2 cos squared theta minus 1. And because we want cos squared theta on its own, we're going to move everything across except for the cos squared theta. So we get 2 cos squared theta equals to cos 2 theta plus 1. And then I'm going to divide through by 2. So we're going to end up with cos squared theta equals to 1/2 cos 2 theta plus 1. And there we have it. We've expressed cos squared theta in terms of cos 2 theta and 1. Now, 1 is just a constant, so that's not too hard to integrate. And cos 2 theta, again, isn't too hard to integrate because we know that when we differentiate 1/2 sine 2 theta, we end up with cos 2 theta. So we know that the integral of cos 2 theta is 1/2 sine 2 theta. Okay. Yeah, it's all good, I think. So then, in this case, if we want to integrate cos squared theta, we can make our lives so much easier by expressing it in terms of what we showed before. 1/2 cos 2 theta plus 1 and d theta. Half cos 2 theta is just going to be that. And then I'm going to leave it as plus 1/2 here. Now usually, or like sometimes you can pull out the half in front, but the reason I'm leaving it in here is because Actually, it might be helpful for us to pull it out. I will pull out the half before we move on. So if we pull out the factor of 1/2, we end up with integral of cos 2 theta plus 1 d theta. And so we end up with 1/2. The integral of cos 2 theta, as we showed up here, is 1/2 sine 2 theta. Plus the integral of 1 is just going to be theta. So it's going to be integral of cos squared theta using our identities, which we expressed in terms of cos 2 theta, is equal to 1/4 sine 2 theta plus theta on 2. And so we're done. That's how you would integrate cos squared theta. Now, I know that seems like a sort of roundabout, longish way to deal with this sort of thing, but it turns out this formula is actually on your formula sheet to express cos squared theta in terms of cos 2 theta, but it's good to be familiar with how to approach or how to get that formula. Yeah, and in the old syllabus, it wasn't actually on the formula sheet, so it's something that you have to derive each time. So I think it's a pretty valuable skill to be able to do. Okay. Here's sine squared x. I already showed cos squared x. Sine squared x is fairly similar, so maybe save some time. I won't go through that one. But yeah, I think that's all we have for today. We do have a bit of time left, so maybe I'll jump back to the quadrilateral example. And that we should have enough time to do this one as well, and that should be it for today. So we'll jump to this quadrilateral vectors example, and that we'll call it day for today. So the quadrilateral ABCD has vertices A, B, C, and D. Show that AD equals BC, and hence explain why ABCD is a parallelogram. Now, just a big tip before we jump into this question. Know your quadrilaterals, know your properties of quadrilaterals. What is a rhombus? What's a parallelogram? How do you define squares, rectangles? It seems a bit obvious, but what happens with diagonals, that sort of thing, because that it can sometimes be part of the question, or sometimes can give you hints in terms of what you need to do and how you need to approach these questions. But for this specific question, we got quadrilateral ABCD has vertices A, B, C, and D, and show that AD equals BC, and hence explain why ABCD is a parallelogram. So we got ABCD. Now I won't yet draw it, and the reason I won't yet draw it is because we don't know which way the labels go. But if we can show that AD equals BC, then we should have a fairly good idea of what the parallelogram looks like. But in this case, I don't know which way it goes, so I'm just going to deal with it in algebraic component form. It's not the best practice in 2 dimensions, but sometimes it's sort of the necessary thing that you have to do. So AD, how do we express AD? Well, it's the vector from A to D. And remember, each of these points have their own position vectors. So it's it's the finish minus the start. That's something that you guys can use all the time. If you've got the vector AD, that's going to be OD minus OA. Now, what is OD? OD is that coordinate vector that we have here, minus 5, 6. What is OA? That's that other coordinate vector that they've given us, 7 minus 5. So then if we subtract those two, we get minus 5 plus 7, which is going to be 2. And we get 6 plus 5, which is 11. Now the next vector that we're asked to show is BC. So let's see what we get when we find vector BC. Same approach. Finish, OC, minus start, so minus OB. So we get OC is 10, 9. Minus OB is 8 minus 2. And so we get 10 minus 8 is 2. 9 plus 2 is 11. So you get AD equals to BC. And so we've shown that AD equals BC, and so we've shown that these two vectors, AD and BC, are equivalent. So we've shown AD. Now I sort of have a rough idea of what the parallelogram looks like. Vector AD and vector BC. Looks like that. They're two equivalent vectors, right? So what happens if we close off these two here? We have vector AB, and we have vector ADC. If we can show that these two vectors are also equivalent, then it's a parallelogram, right? Now there is a couple of ways of approaching this. You can use the parallelogram law of addition to show that it's a parallelogram, but I think it's easier to show that AB and DC are the same because it's pretty much the same process, just with different numbers. If you show that they're the same, we've shown that they're equal in length and they're parallel. So we've got two pairs of parallel sides. So we've shown that these two are parallel and are of equal length. If we can show that the other two sides are equal length and parallel, then we're done. Then we've shown that it's a parallelogram, just by properties of parallelograms. So let's show that AB. Let's see what AB gives us first. Vector AB is OB minus OA, which is the end minus the start. And you can double check that by using your vector subtraction sort of laws, the geometric approach. It should give you the exact same thing. So OB is 8 minus 2, minus OA is minus 7 minus 5. So 8 plus 7 is 15. Minus 2 plus 5 is 3. So 15, 3. And what does vector DC give us? Vector DC is OC minus OD. Well, that's going to be OC is 10, 9. Vector OD is minus 5, 6. So we end up with 10 plus 5, so 15. 9 minus 6 is 3. So we've shown that AB is equal to DC. So therefore, we've shown that, coming back to our diagram, these two vectors are parallel. They're also of equal length. So we've concluded that because they're equal, just by definition of vectors, if two vectors are equal, they have the same magnitude and direction. Vector AD, we can talk about magnitudes first maybe. Magnitude of AD equals to the magnitude of BC, and AD is parallel to BC. We've also shown that AB is the same length as DC, or CD, either however way you want to put it, and vector AB is parallel to DC, not the magnitude, sorry. AB is parallel to DC, like this. And so we've shown that we've got two pairs of sides which are equal length and parallel, and therefore it must be a parallelogram. And that's that. We've proven that it's a parallelogram. Hope I spelled that right. It looks right, I think. But that's it for that question.